We are dealing with estimating parameters and determining sample sizes. Now we're going to look at the same concept. So a point estimate is a specific numerical value estimate of a, as it was mentioned. The point estimate is a single value. The point used to approximate a population parameter. In the case of a mu, we use X bar. So the sample mean X bar is the best point estimate of the population mean mu. So we use X bar, we make up a confidence interval based on a sample given to get to the confidence interval estimate of the true value of a population mean. We can also find the sample size that is necessary to estimate a population mean.
Verify that the two requirements are satisfied. The sample is a simple random sample and the population is normally distributed, or n is greater than 30. Sigma is unknown, use t distribution. Sigma is known, use z distribution.
Deal with a case like this as far as the mean is concerned. Either sigma is given or not. By the way, most of the time sigma is really not known. I want you to know that. In fact, in some tags, they almost stop talking about the z. So sigma is given, the population standard deviation. We can use the z distribution. If it's missing, we use a t distribution. So that's the main thing I want you to worry about. As far as the requirements, and most of the time, decent sample should be a simple random sample. Now, if the population is normally distributed, we are in good shape. If it's not, then n must be large. And as you recall, how large is large enough? If it's larger than 30. That's CLT. And so with that being the case, we're going to come up with a confidence interval for estimating a population mean when sigma is known. The requirements, again, we're going to repeat that. The sample is SRS, short for simple random sampling. And it's either normally distributed or n is large. By large, of course, we mean larger than 30. Mu is the population mean. N is the number of sample values, just the number of sample size or data. X bar sample mean. E is the margin of error, and S is the sample standard deviation. Now, we use DF, degrees of freedom, to be n-1 is the number of degrees of freedom used when finding the critical value. Critical value, instead of Z alpha over 2, we use T alpha over 2 when sigma is missing, separating an area of alpha over 2 in each take, right and left. That is to use the student T distribution, or simply put, we call it T distribution. Now again, X bar plus minus E, that is the formula that is used. And the margin of error, notice this one is very close. When we used for the P for P, we use P hat. Now for the mean, we used P hat was the point estimate of P. Now, what is the point estimate for the mean mu is X bar. So X bar plus minus E. And so T alpha over 2 S over square root of n, this is the margin of error. This is called S sub X bar. And we add and subtract this E to get to the confidence interval. Sometimes we use X bar, X is capital, sometimes it's not, but that's really not the big deal. The only thing I want you to pay attention is the following. Sigma is not known. Sigma is not known, and that's the idea, okay? All right, because if it is known, we use the Z table. And we will discuss the T table as we come across it shortly. All right, so T distribution is being used in most cases simply because standard deviation is missing. So dealing with the student T distribution, if a population has a normal distribution, the distribution of T equals X bar minus mu over S over square root of n is a student T distribution, or simply put, T distribution for all samples of size n. A student T distribution is commonly referred to as T distribution. In general, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. Degrees of freedom is defined as n minus 1. Now, when we use technology, we have access to the answer. That's fine and dandy. But if you're using this t-table, the t-table is limited, and therefore, if the degrees of freedom is not there, the table, then it will be conservative to go to the next one. And the next one, you really want to go with the closest one. Up and down is fine, but if you have a choice, you want to go to the lower one. I would always choose the closest number. Again, if it's in between, we would go with the one below.
The t-distribution is similar to SND. It is bell-shaped, it is symmetric about the mean. The mean, median, and mode are equal to 0 and are located at the center of the distribution. The curve never touches the x-axis.
It's very close to Z. It's bell-shaped and it's symmetric around mu, the mean and median and the mode occur at the same point, namely 0.
The t-distribution differs from standard normal deviation. Variance is greater than 1. The t-distribution is actually a family of curves based on the concept of degrees of freedom, which is related to sample size. 3, as the sample size increases, the t-distribution approaches the standard normal distribution.
The idea is that t ultimately becomes z and is log. In some texts, they use z instead of t when n is large. In fact, when n is larger than 30, because those values are extremely close. They don't do that nowadays. And again, it really depends on the text. But it used to be that in most texts, they would use the z values when n was large. And if you look up the table, you see they are fairly close. It is bell-shaped and it becomes, for all practical purposes, z distribution if n is large. We have seen how to look up the z table. Let's discuss the t table. What we want to do here, we want to find the critical value corresponding to 95% confidence interval for n equals 15. I like to do the drawing first, just to give you an idea. Again, looks like a Z. We have this shape. For each tail, we have 5% divided by 2. Let's make sure everybody understands how we get to 0.025. Again, I want to make sure nobody makes a mistake. So we have a 95% confidence interval right smack in between. This is 95%. It's in the middle. And again, when you do the drawing, it may not be too scary, it doesn't matter. So the rest of it, that means 5% covers the two tails. So each one is 5% divided by 2. And that's how we arrive at 0.025. So now, how do we read the table? The table starts reading with the degrees of freedom. So degrees of freedom is n minus 1. So if degrees of freedom is given, so be it. If not, it's n minus 1. 15 minus 1 is 14. So you would start with the left column, degrees of freedom. So you look at degrees of freedom column, pick the number. Now you go across, one of them is the answer. Which one is the answer? When you look at your confidence interval is 95%. The area in one tail is 0.025 and in two tails is 0.05. And you put them together, you have the answer. So degrees of freedom is 14. 95% confidence level, alpha is 0.05, area in each tail is 0.025. So you look at this number, 14. You look at here, area in one tail is 0.025, or in two tails is 0.05. This is your answer, which means what? Plus, minus. There are two of it. Okay, by the way, when you look this up, even if it happened to be a left tail test, we discussed that when we do the test of hypothesis. And you read that, you should recognize that means negative. So this is plus minus 2.145. This is using the table. We can use technology, whatever technology that you have is fine. As an example, if you use a TI, so to find the t-score, second variables, inverse t, you put two entries, left, area, and degrees of freedom. So take a look. Inverse t, area to the left is 0.025, degrees of freedom is 14. And look at the number. If you do the rounding here, that means you look at the next number, which is 7, and you change this 4 to number 5. Let me show you calculator. We click on second variables. We bring it down to inverse t. Now area is on the left side, 0.025. Degrees of freedom n minus 1, 14. Okay, that's how we arrive at this. Enter. It shows you inverse t. Area to the left is 0.025. Degrees of freedom is 14. And you enter, and it does the calculation for you. Negative 2.144786681.
Does garlic lower cholesterol levels? To test the effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. The changes in their levels of LDL cholesterol in milligrams per deciliter have a mean of 0.4 and a standard deviation of 21.0. Use the sample statistics of n equals 49, x bar is equal to 0.4, and s is equal to 21.0 to construct a 95% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. What does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol?
You need to start with the given. It's all in proper notation, and we want a 95% confidence interval. Because n is large, by large we mean larger than 30, we can use the proper table. Now before we discuss the proper table, as you all can see, sigma is missing. And because of that, we are going to use the t distribution. So the very first thing we look at the drawing of 95%. You do that regardless if you need the z or t or you name it. Now, to find the t value, you go to the t table and you look up degrees of freedom. So what happens is that n is 49, degrees of freedom is 49 minus 1. Now, when you look at the table, and we'll bring it up in a moment, the table doesn't have number 48, at least some do, okay? Most of them don't. So if it does have it, so be it. If not, you come up with the closest number. 50 is closer to 48 than going down. And because of that, we stick with 50. And that reads negative 2.009. We are using the table. I'll share the table in a moment. I think you should all pick up the table, look at it, convince yourself you can do the reading. And so with that being the case, all we have to do, calculate the value of E. And E is T alpha over 2 S over square root of N. T alpha over 2 S over square root of N. And you do that with a bunch of decimals. By the way, don't do the rounding earlier. You really can't emphasize this enough. You have to do it at the end when you want to turn in your answer, but in between your calculations, you want to keep as many decimals as you want, or your calculation will be wrong. So having said that, you calculate the value of E, and all you have to do, x bar is 0.4, add and subtract this number. Subtract from 0.4, add to 0.4. And so this is the confidence interval. So what? Now we got the confidence interval. What does it mean? Do we understand what that means? And that is extremely important, understanding what we are doing. So first, as far as the concept of a confidence interval is that we are 95% confident that this interval contains the true mean. So we are 95% confident that the limits of negative 5.6 and 6.4 actually do contain the value of mean, the mean of the changes in LDL cholesterol for the population. What does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? So this is the case. This is the reason.
The confidence interval limits contain the value of 0, so it is possible that the mean of changes in LDL cholesterol is equal to 0. This suggests that the garlic treatment did not affect the LDL cholesterol levels. It does not appear that the garlic treatment is effective in lowering LDL cholesterol.
When you look at this confidence interval, three things happen. Either we go from negative to positive, which means 0 is included. If 0 is included, there is no effect. Or both sides are negative, that means it makes it worse. Or both sides are positive, that means it helps. This is the idea behind using the confidence interval. The thing I want to add here, this is absolutely fine. If both of them are negative, that means the LDL level of cholesterol is going down. Both numbers are negative, it's going down, and that means, yes, it is effective. Both numbers are positive, that means it actually takes the cholesterol up, makes it worse, positive, because this is the mean net change in LDL. So I'm going to repeat, when 0 is in between, there is no effect. Now, if you're using a drug, just for the sake of argument, some medication, we are checking some medication, we want to see if it takes it down, it's better, that means it does have an effect. In this case, taking it down is better. If taking it up is better, both of them are positive, okay? So in this case, if the cholesterol LDL level goes down, it's better, therefore, that means effective. So both numbers must be negative for it to be effective. All right, so having said that, here's another one, confidence interval, T interval. You go to calculator, stat, test, T interval, and you enter data or stats, and then you calculate. What do you put in? X bar, S, N, confidence level. Now take a look at the answer. Now the answer obviously is very close to what we have. Why are they different? Because we use the table and we guesstimated the T value. They are using technology and they don't have to. So first, this is a table you have access to, Z and positive Z score. The top one was negative. And now we are looking at the T table. So notice we are going down. I'm looking at the very first column, 1, 2, 3, and we go down. And notice what happens. We have all the way to number 40, and that's good. Then it goes to 45, then it goes to 50. And there is no number 48 there. Remember, N was 49, degrees of freedom was 48. And because 48 is closer to 50, we choose that one. And so just going back up there, just after the first column, the second, the third, the fourth. Look at the fourth column at top of the fourth column. Area in one tail is 0.025. And in two tails is 0.05. So that's why we go down to 50, and then this fourth column, and it's 2.009, and we picked that one. So T is plus minus 2.009 as far as the two values are concerned, because remember we have on the negative side and on the positive side. And let's also quickly look at the technology. So what we want to do, we want to click on stat, and we go to the right side, tests, Z test, T test. Okay, now everybody can see the T interval. Now you have a choice of using data over here or stats. Data, when let's say you have 10 pieces of data and you use that, you put it in L1, let's say. First you enter the data in somewhere like list 1, L1, L2, whatever, and that's where you put the data. In this case, it's stats. So put X bar equals 0.4. We enter. S, again, to be precise, is S sub X bar. N is 49, and confidence level is good, 95% or 0.95, and we do the calculation. And so it gives us the answer, negative 5.632 to 6.4319. That's what we had. Now, let's look at another example.
10 randomly selected people were asked how long they slept at night. The mean time was 7.1 hours and the standard deviation was 0.78 hours. Find the 95% confidence interval of the mean time. Assume the variable is normally distributed.
It's important to read and write the given. For example, the very first number is 10, so that's your n. The next number is 7. It says it's the mean, so x bar. Remember, why is it x bar and it's not mean? I want to make sure everybody understands. 10 randomly selected people were asked how long they slept that night. So 7.1 pertains to those 10 subjects. And those 10 subjects have a standard deviation of 0.78. And that is S, 95% confidence interval. And assume normally distributed. So with that being the case, we know it's a normal distribution. We know n is 10, x bar is 7.1, s is 0.78, and 95% confidence interval is of interest to us. Let's make up the confidence interval. To do that, you have to go to the t table. Degrees of freedom is n minus 1 or 9. I highly recommend you. And so we end up with t being 2.262. Again, perhaps graphing would be helpful. Again, those are the tails, and this is 95%. You calculate the E, which is T alpha over 2S over square root of N, or just you write it in this fashion. This is another way of writing it. Instead of calculating the E only, you can write it in this fashion and do all of it in the same shot. And then subtract from X bar, add to X. That's good enough. But just the way it is, we plug in. That's why the given is important. I don't have to think twice. I go to the given and I plug in all the given that I have written. So you know what's the given symbolically. You just plug in. So we plug in those numbers and we calculate this part. This becomes 0.56. By the way, generally speaking, they add one more decimal. But I highly recommend you put a lot more just to be on the safe side. The rounding takes place at the very end. And so do the math. We end up with 6.54 less than mu, less than 7.66. How we would word this out? You constructed a 95% confidence interval. What does it mean? If you were to verbalize this, how would you write this for your readers? So you can repeat the wording. If you remember, basically you just repeat the wording in a sense. We are, whatever the confidence interval says, 95%, 90%, 99%. So we are 95% confident that the limits of 6.54, and remember those are, let me just write the units, hours. The limits of 6.54 hours and 7.66 hours actually contain the true value of mu, okay? The mean value that people sleep at night. So we are 95% confident that the true value of the mean mu that people sleep is between 6.54 and 7.66 hours. In the case of P hat, it worked out the same thing. Now, instead of P hat, X bar works out this way. And again, the reason being is very simple. Remember, the confidence interval is from X bar minus E to X bar plus, all you have to do, add these two and divide by 2, it gives you X bar. If you add them up, E and negative E cancel each other, 2x bar over 2, and that's X bar. On the other hand, if we subtract them, that means the left side, X bar minus E, subtracted from the right side, X bar plus E, it gives you 2E divided by 2E. So that's how you get to the margin of it. What happens when sigma is known? In short, we use the Z table. And so with that being the case, we have a similar way of calculating this. All of that, the T goes to Z. And the reason we mentioned the T first, because most of the time, we really don't have access to sigma. So that's how we arrive at it. E is Z alpha over 2 sigma over square root of N. Now, we want to calculate the sample size. What is the sample size required to get to this estimate? In this case, you use this one, and you solve for N. To solve for n, let's square both sides. E squared equals, for short, I'm going to just write z. So z squared, sigma squared, and square root of n simply becomes n. One way to do the cross product, you can interchange n and e squared, and this is the value of n, and that's how you calculate. We're going to go to the next example.
People have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. The mean weight of men has increased considerably, so we need to update our estimate of that mean so that the boats, aircraft, elevators, etc. do not become dangerously overloaded. Using the weights of men from a random sample, we obtained these sample statistics for the simple random sample, n equals 40, x mean equals 172.55 pounds. Research from several other sources suggests that the population of weights of men has a standard deviation given by sigma equals 26 pounds.
Now, as far as the question is concerned, everything is given symbolically in x bar. And what is really important is that you have S or sigma. And again, symbolically, they are giving us sigma. And that's extremely important. So it's either normally distributed or it doesn't matter, n is large. Either way, we can use that because sigma is given when we are looking at that E instead of T alpha over 2 S over square root of n, we're going to use Z alpha over 2 sigma over square root of n. So that's the first one. Now, what is given? It's a random sample. N is 40, which is larger than 30. X bar, sigma, 95% confidence interval. Let's go step by step. The very first step is asking us to come up with PE, short for point estimate, mean. That means point estimate of mu. And point estimate of mu is X bar. That means to get started with confidence interval, we start with somewhere. And that somewhere would be this X bar sample. The next thing is we want to come up 95% confidence interval, and graphing is really, really helpful. I highly recommend that. So to do that, it's one of those common ones that we've seen, or we can go look up the Z table, and that becomes plus minus 1.96. But again, you can look it up. So E is Z alpha over 2, 1.96, times the fraction bar. The top is sigma, 26, and the bottom is the square root of n, which is number 4. Now you simplify and you have this number as E, you subtract it from X bar, you add it to X bar. And this is your confidence interval. This is the confidence interval. What do the results suggest about the mean weight of 166.3 pounds? First of all, just in short, if we were to discuss this confidence interval, we would say we are 95% confident that the true mean weights of men is between these two numbers, 164.49 and 180.61 pounds. What do the results suggest about the mean weight of 166.3? Notice 166.3 is in between. So based on this data, it could happen that the mean is in between. But notice it's extremely close to the left. That's another thing that is important.
Based on the confidence interval, it is possible that the mean weight of 166.3 pounds used in 1960 could be the mean weight of men today. However, the best point estimate of 172.55 pounds suggests that the mean weight is now considerably greater than 166.3. An underestimate of the mean weight of men could result in lives lost through overloaded boats and aircraft. These results strongly suggest that additional data should be collected.
Quickly look at technology and how it's taken care of in case. I put those stuff so you can have a chance to look at it and compare and see that technology can be used if need be. That's taken care of. We're going to go to the next one.
A researcher wishes to estimate the number of days it takes a car dealer to sell a particular brand of car. A sample of 50 such cars had a mean time on the dealer's lot of 54 days. Assume the population standard deviation to be 6.0 days. Find the best point estimate of the population mean and the 95% confidence interval of the population mean.
Let's write the given. And the very first one is number 50, a sample of 50, so that's n, and it's larger than 30, so that's good. Then mean time, that means x bar. And then we have population standard deviation, sigma. And we want a 95% confidence interval. Point estimate for mu is always x bar, so that's not a big deal. Point estimate is always x bar. Now, we want to find the confidence interval. In general, it's x bar plus minus e, but what do we use for e? Do we use e equals t alpha over 2 s over square root of n, or e equals z alpha over 2 sigma over square root of n? Which one do we use and why?
Can you repeat the question?
Okay, we know in general when we deal with the mean, to find the confidence interval, we use the formula x bar plus minus e, no problem. Now, for e, which one do we use? The one which is t alpha over 2 s over square root of n?
Wouldn't we use the z distribution because we are given sigma?
Absolutely. Because sigma is given, we use z alpha over 2 sigma over square root of n. So this is the reason you want to write the given symbolically, and you want to read and reread the question to see what is given. Okay, if sigma is missing, you go to t. When it's given, you go to z, and that's extremely important. So by now, again, it's the z value for 95% confidence interval, very straightforward. We know it's plus 1. So this, okay, let me write this in fact, because this is negative 1.96. This is positive 1.96. And remember, we have really a plus minus. That's where it comes from. Minus and plus 1.96. So we do the calculation. By the way, I'm showing you, if you use technology, you can come up with that at 1.96 here. Okay. Using this formula, 54 minus 1.96 times 6 over square root of 50, and then 54 plus the same thing. So all you have to do, calculate this one, subtract it from 54, add it to 54. Again, I would use more decimals, but I do the rounding at the very end. This has been rounded properly, but be careful. You don't ever want to take a chance. So the answer is this. What is this referring to? It says a researcher wishes to estimate the number of days it takes a car dealer to sell a particular brand of cars. Because it is specifically asking for the number of days, you can answer it accordingly. Therefore, the rounding is done accordingly. So 52.3 becomes 52, but 55.7 goes up to 56. If you left it as 52.3 and 55.7, it would be fine with me if you're doing it. Let's go to the next one.
A survey of 30 emergency room patients found that the average waiting time for treatment was 174.3 minutes. Assuming that the population standard deviation is 46.5 minutes, find the best point estimate of the population mean and the 99% confidence of the population mean.
Okay, the very first thing we want to see, what's given symbolic. So a survey of 30. So that's the first number we come across, n is 30. The average waiting time, that's x bar. Why is it x bar? For those 30 people, the average time was 174.3 minutes. So we are assuming the population, okay, so let's see, population standard deviation. And as you can see, this is sigma. And we want to find point estimate, and we want to find 99% confidence interval. We write the given properly. That's extremely important. So random sample. N is 30, X bar is 174.3, sigma is 46.5, again the units minutes. And we are interested in finding the confidence interval accordingly. Number one, what is the point estimate? For mu, it's always X bar. That's a 99% confidence interval. And then 1% divided by 2 gives you 0.005 on each side. So 99% confidence interval. 1% left in both tails, you divide it by 2, it gives you 0.005. So the very first thing, the point estimate is very clear. And now we are dealing with 99% confidence interval. You're using the z-score, so I hope everybody remembers. Again, this is one of those common ones, and we can look them up. So this one is negative 2.575. This one is positive 2.575. So all you have to do, calculate the value of E, add and subtract the value from X bar, and you're done. So we can write it in this fashion, for example, or we can just calculate this part. All you have to do, calculate this part first, add it to X bar, which is 174.3, subtract it from X bar. So when we do that, subtract it and add it, it gives us the following. Could somebody tell us what this means? And if you were to do the writing for your readers, how would you write this? Anyone want to share with us? How would you write this for your readers after you've done the work?
It's like the accuracy of with the standard deviation because of how small the population is.
I want you to tell me about the confidence interval. We are
99% confident that the average waiting time lies in the interval between 152.44 and 196.16.
We are 99% confident that the true value of the waiting, the average waiting mean, so this is in minutes, it's in between the two values. We are 99% confident that these two values contain the true mean for the waiting time for treatment in an emergency.
How many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? Assume normal distribution with sigma equal 15.
We want to make sure we understand what's given. So as we look at the question, the very first number is 95% confidence, okay? So that's the 95% confidence interval we need. The sample mean is within IQ points. That is the maximum margin of error. And of course, 95% is one of those common ones. By now, we know the answer is 1.96. So all we have to do, use the formula at the top right in blue and replace the numbers accordingly. By the way, at the end says assume normal distribution, sigma is 15, it's given symbolically. So you just plug in those numbers and you square. Now remember what happens when you're dealing with this case. How many do we need? What is the number size? What is the sample size we need? That means we need 96.04 at least. And regardless, in a case like this, with the proportion also, you have to round up. So n is 97. So I highly recommend you write the answer 96.04 and then box the answer 97. So you want to show your reader that how you arrive at 97. First you calculate 96.04, then you round up because we have to.
The scientist wishes to estimate the average depth of a river. He wants to be 99% confident that the estimate is accurate within 2 feet. From a previous study, the standard deviation of the depths measured was 4.33 feet. How large a sample is required?
99% confident. So we want a 99% confidence level, we want a 99% confidence interval, and that obviously is one of those common ones, the z-value 5, 8, and within 2 feet, that's maximum error, or margin of error is E. And then from a previous study, the standard deviation of the depth measured, so that means we are assuming this is sigma. We are assuming this is sigma. And so we use 99% confidence interval, which corresponds to about 2.58, but it's really 2.575. The reason you don't want to use that because it's one of those values we even have this in the table, 2.575. Stick with the numbers that are given. The reason they have given us that number because it's one of those common ones we come across often. So stick with 2.575. So you go to the top right formula, you plug in the numbers. So 2.575 times 4.33 over 2, and you divide it by 2. It's important to keep it as 2.575, otherwise the numbers will be different. So this gives us 31.07. You want to write it with one or two decimals. Understand that we need a decimal, and therefore, according to this, it has to go up to number 32. So again, you show this to your reader, and then you take it a notch up, just to be on the safe side. I want to go to the next section, but let me spend a couple of minutes on the next example, just quickly. You can read this on your own, but I want to make a point. Given the following random sample, for n equals 15, x bar is 30.9, and sigma is 2.9. For birth weights of children, construct a 95% confidence interval of the mean birth weight of all years. So with that being the case, notice what's happening here. For this section, if you want to use it, remember n has to be large, or it has to be normally distributed for us to. It doesn't say it's normally distributed. N is not large, it's only 15. And so how do we deal with that? So I just wanted to mention that, okay? So at the very least, you've seen that. So with that being the case, you basically check the normality. So you look at the requirements, simple random sample, N must be larger than 30, and it's not. And the thing is, N is not. So you have to investigate normality. I'm not going to go over that. We've seen this before. Remember, the X and the Y value is the Z-score. Remember that? And because it's almost normally distributed, then you can use the formula. If we come across a case like that out there, you're doing your research, you want to do this, you have to check the normality. And so now you calculate the E using the fact that sigma is given as 2.9. You add and subtract this to x bar, and this is the confidence interval. Again, I'm mentioning this just for the sake of argument in case we come across a situation where n is not large and we are not sure if we are dealing with a population which is normally distributed.